Wood science and technology. Mesoporous bulk wood structures for catalytic contaminant removal. Bulk wood materials can be directly utilized and modified for water treatment. Mesostructured natural wood with long and aligned channels enables high rates of water and ion transfer. The high surface area with abundant hydroxyl groups in cellulose can act as active sites for adsorption and catalyst immobilization. When decorated with catalytic nanoparticles, wood can be used as a microreactor for in situ contaminant degradation. The first attempt to functionalize bulk wood for water treatment was by decorating basswood with PD nanoparticles to reduce methylene blue, MB. The modified wood was used as a flow-through reactor for dye-containing water filtration, achieving up to 99.8% MB removal and a maximum flux of 105 LMH. Similarly, radiata pine sapwood decorated with Ag nanoparticles was effective in MB reduction and bacterial inactivation. Chemical oxidation using carbonized fir wood loaded with Mn3O4-TiO2 nanoparticles also showed high MB removal efficiency, but lower than the catalytic reduction process. Another study used a similar approach to make a hybrid material composed of femino nanosheet and wood carbon using carbonized basswood, which achieved more than 95% degradation when treating 20 ppm MB. The image shows the effect of Mn3O4-TiO2 nanoparticle loading on the MB removal efficiency of the modified wood. Bulk wood materials can be functionalized with catalytic nanoparticles for water treatment. Flow-through reactors made of modified wood have shown high efficiency in removing MB and other contaminants. Both catalytic reduction and oxidation reactions can be used in these reactors. More development and analysis are needed to understand the reaction mechanisms and investigate more emerging contaminants in water. In addition, the reduction process using NABH4 produces bromate as a side product, which is a potential human carcinogen. The oxidation process using hydrogen peroxide does not produce any toxic side products. The image shows that the MB removal efficiency increases with the loading of Mn3O4-TiO2 nanoparticles. Cellulosic composites and functionalized bulk wood for chemical adsorption. Cellulosic composites and functionalized bulk wood are promising adsorbents for contaminants such as heavy metals, dyes, hydrocarbons, and dissolved organic compounds. Cellulose nanofiber mats can be grafted with polyacrylic acid to enhance their strength and binding capacities to heavy metal ions. Block copolymer poly-3-trimethoxysilyl propyl acrylate block myrcene can be grafted onto cellulose membranes to turn them from hydrophilic to hydrophobic, giving them excellent oil absorption capacities. Bulk wood filters can be chemically treated to add carboxylic acid groups, which can be used to adsorb heavy metal ions such as copper. Bulk wood can be delignified and then modified with chemicals to give it hydrophobic and oleophilic functionality, making it an effective adsorbent for oil and organic solvents. Wood epoxy biocomposites prepared by polymerizing epoxy solution on the delignified balsa wood template exhibit both high Young's modulus and yield strength, as well as excellent oil and organic solvent adsorption capacities. Hydrophobic wood sponges prepared by grafting polysiloxane on the wave-like stacked wood structure using chemical vapor deposition demonstrate much higher oil and organic solvent adsorption capacities beyond 15 GG1. The saturated wood can be easily compressed to recover the oil or organic solvent, making the wood material reusable with longevity in performance. More studies are needed to test and optimize the materials for use in real conditions, where water may be contaminated with multiple pollutants. Carbonized wood for energy generation from wastewater treatment. Carbonized wood is a promising material for electrochemical applications, such as electrodes for microbial fuel cells, MFCs. Carbonized wood has a high surface area, hierarchical mesoporous structure, high conductivity, and low tortuosity, making it ideal for hosting electrochemical reactions. Compared to traditional graphite-based electrodes, carbonized wood electrodes have a lower weight, doubled surface area, and higher conductivity. The unique hollow structure of carbonized wood electrodes allows for dual surfaces for microbial electron transfers, which leads to much higher power output. Carbonized wood electrodes can also be used as 3D microfiltration membranes to improve MFC effluent quality. A study by Huang et al. Showed that a carbonized wood membrane, a node, could remove more than 90% of the chemical oxygen demand, SOD, total nitrogen, TN, and total phosphorus, TP, in brewery wastewater, while generating 204.8-295 MWM2 power. The image shows a carbonized wood membrane anode with long and well-aligned channels. These channels allow for high water permeability and good removal performance, as well as cell acclimation without blocking water flow. Overall, carbonized wood is a promising material for energy generation from wastewater treatment. It has the potential to improve the performance and efficiency of MFCs, while also reducing costs. Nanowood for energy-efficient water desalination and environmental remediation. Trees play an instrumental role in the global water cycle by evaporating water to the atmosphere using sunlight as the energy source. Researchers are mimicking this solar evaporation process using functionalized bulk wood materials to develop renewable energy-driven desalination devices. The long vessels in wood ensure fast water transport, while the anisotropic pore structures provide excellent thermal insulation. Solar-driven desalination using wood evaporators has great potential compared to existing technologies that rely on fossil fuel-based energy and materials. Wood evaporators can also be used for resource recovery and environmental remediation. The image shows a conceptual diagram of a solar-driven desalination device using a wood evaporator. The wood evaporator is coated with a light-absorbing material, such as carbon nanotubes or plasmonic nanoparticles. When exposed to sunlight, the wood evaporator heats up and evaporates water from the underlying saltwater reservoir. The evaporated water is then collected as clean water. Overall, wood evaporators are a promising new technology for renewable energy-driven water desalination and environmental remediation. Wood evaporator for high-efficiency solar thermal desalination. Solar energy is an unlimited source of renewable energy, but traditional solar-based desalination methods are inefficient. There is a great need for fresh water, and researchers are developing new desalination technologies to meet this demand. Wood evaporators. Wood evaporators are a promising new technology for solar-driven desalination. Wood is a sustainable and abundant resource, and it has many desirable properties for solar evaporation, such as low density, high porosity, and low thermal conductivity. Key advances in wood evaporators. Researchers have developed wood evaporators with high evaporation rates and efficiencies. For example, one study achieved an evaporation rate of 1122 kgm2H1 and an evaporation efficiency of 81% using a wood evaporator coated with carbon nanotubes. Another study achieved an evaporation rate of 1.2 kgm2H1 and an evaporation efficiency of 80% using a reverse tree wood evaporator. Advantages of wood evaporators. Wood evaporators are low cost and easy to fabricate. They are also scalable to large sizes, making them suitable for commercial applications. The image shows a reverse tree wood evaporator. The wood evaporator is placed with the growth direction laid down parallelly to the water surface. This way, water is transported across vessel walls via the numerous small pores called pits. The layered channels in the direction perpendicular to the growth lumen direction carry much lower thermal conductivity. In conclusion, wood evaporators are a promising new technology for solar-driven desalination. They have the potential to provide a sustainable and cost-effective way to produce fresh water from saline water. Nanowood membrane for thermally efficient membrane distillation. Nanowood membranes are a new type of membrane that is being developed to replace polymer materials for efficient membrane distillation, MD. Membrane distillation MD is a water separation process that is driven by low-grade heat from solar thermal, geothermal, or waste heat sources. Nanowood membranes are made from delignified wood materials which have a highly hierarchical pore structure that allows high vapor permeability and low thermal conductivity. In tests, nanowood membranes were shown to have intrinsic vapor permeability and thermal efficiency that were higher or comparable to commercial polymer MD membranes. The main challenge with nanowood membranes is their thickness, which is currently around 500 compared to around 100 for polymer membranes. Future research will focus on developing advanced manufacturing processes to enable the production of larger and thinner nanowood membranes. The image shows a schematic of a nanowood membrane for MD. The membrane has a highly hierarchical pore structure that allows high vapor permeability and low thermal conductivity. The membrane surface is treated to be hydrophobic, so vapor can pass through, but the liquid will be retained. Overall, nanowood membranes are a promising new technology for efficient MD. They have the potential to replace polymer membranes in MD applications, which would reduce costs and improve the environmental sustainability of MD. Wood evaporator for oil contamination remediation. Wood evaporators have several advantages for oil contamination remediation. They can quickly heat oil-water interfaces to temperatures that make oil less viscous and more easily removable. They have low tortuosity, which allows for efficient oil flow into the evaporator channels. They are efficient at converting solar energy into heat. Wood evaporators have also been shown to be effective for groundwater remediation. They can achieve evaporation rates of over 11 kgm2h1 and evaporation efficiencies of over 80%. They can remove ions and bacteria from water, leaving behind clean groundwater. Overall, wood evaporators are a promising new technology for oil contamination remediation and groundwater remediation. They are cost-effective, sustainable, and effective at removing pollutants from water. Fouling control and long-term operation. Fouling, scaling, and long-term stability are important concerns for filters and membranes used in water purification systems. Salt precipitation can occur on the surface of wood evaporators due to the rapid evaporation of water. Bimodal porous structures in balsa wood can help to limit salt crystal formation. Artificially drilled holes in wood evaporators can create a self-balance mechanism that redistributes salt concentration inside the wood substrate. Hydrophobically treated nanowood MD membranes can be used to treat highly contaminated and/or high salinity streams, such as wastewater and seawater. Physical and chemical cleaning may be necessary to maintain the flux of nanowood MD membranes. More research is needed to understand the fouling behavior of wood-based water purification systems and develop strategies to reduce fouling and extend system longevity. Overall, wood-based water purification systems have great potential for desalination and wastewater treatment, but more research is needed to address the challenges of fouling and scaling. Outlook. Wood materials have the potential to replace petroleum-based materials for water and associated applications. Advanced nanomanufacturing has increased the value and functionalities of wood materials. Further development is needed in improving material uniformity, stability, and functionality. Scalable reactor systems need to be developed to treat actual impaired water streams. More effective modification methods and testing protocols are needed to maintain the quality of the materials. Effective cleaning and regeneration methods need to be developed to mitigate fouling and extend material lifespan. More testing and modifications will be desired using actual contaminated water samples and operate reactors in engineering-related conditions. The size of the wood materials needs to be scaled and production needs to be streamlined. Long-term stability of the materials needs to be tested under various conditions. Technologies need to be developed to treat and reuse the water and recover metal, energy, and other resources from the waste stream generated during nanowood fabrication. There is great promise in using nanowood materials to achieve effective separation and recovery of value-added products from water. New types of wood membrane electrodes can be fabricated to replace polymer membranes and recover gaseous products such as H2NH3CH4 for waste valorization. Overall, wood materials offer a promising and sustainable alternative to petroleum-based materials for water purification and related applications. Thanks for watching, and don't forget to hit that like button, subscribe, and hit that notification bell for more content.